So this bit right here, we had gotten down to, we had gravitational energies converted to some translational, some rotational. We look at a point of mass on this circle. Maybe it's the hoop. It could be modeled as the hoop. And then that piece of mass has its own velocity. V is equal to r omega. We substitute that in for our 1/2 mv squared, and we have r omega all squared. Distribute the squared business, and you'll have mr squared and omega squared. And the v squared and the omega squared are analogous to each other. For every translational value we have studied all year long, there is a rotational analogy. So if you can have a linear velocity, you can have an angular velocity. If there is a linear acceleration or translational acceleration, there's an angular acceleration. If there can be translational kinetic energy, there can also be rotational kinetic energy. So for every linear or translational value that we've learned this year, there's a rotational analogy. So it turns out that it's not just the m, but it's where the m is that matters. So this is like our rotational analogy for mass, the moment of inertia. It's more than just what is the mass of the object, but where is the mass of the object located. And so every different shape has a different value. So for a hoop or a point mass, so if here is a center and here is a cord, a light skinny cord, and here is maybe a tennis ball or this little wiffle ball I have here that's on this yellow string, it's like a particle. Okay? It has all of the mass in one place, and all of that mass is at a distance r, the length of the string, away from the rotational point where my fingers are touching it. And so that it has a moment of inertia. It has this m at a particular r. So for a point mass going round and round, because all of the mass is concentrated at the same position, the moment of inertia would be mr squared, just like modeling it for our rotational analogy. All right, so the disk is another example, not a disk, pardon me, a hoop. So a hoop, I'm looking at the side view of a hoop, like the one we rolled down the wooden inclined plane today, and it has a radius of r like that, and it's rotating about the z-axis. So think about x being horizontal, y being vertical, z coming out of the page at you. That's the z-axis. And so if it's rotating like this, then the moment of inertia of that, because all of the mass is located at the same position, you could concentrate it and think about it as just being a particle, add up all the little bits of mass, and it's the total mass of the hoop, and it's also mr squared. So that's kind of nice. Now, what did you notice about the disk? The disk didn't need as much of the gravitational energy. Therefore, it had less rotational energy, and less rotational energy means that it had a smaller moment of inertia. It needed less of that gravitational energy. So a solid disk imagine, whoops, I was going to try to make that solid. So a solid disk, where this is r, rotating like that, it's not mr squared, it's less. It's less by a factor of 1/2. If it has a uniform density. And that comes from the integration, but you're not responsible for that. Don't worry about it. You will be given all the moment of inertias for funny shapes that you ever need. The one you should take to be your own and remember is the particle, mr squared for a particle. You should be able to remember that that's the moment of inertia. But for a disk or a sphere or a cylinder or a thin hollow sphere like a ping pong ball, those will all be given to you. Okay? You don't have to try to memorize this table. And you can make a quick Google search, but for moment of inertia, and there's all kinds. I did the image search, and there's tons of moments there, and they have the different axes. So what I was saying about the z-axis, so this is like the hoop, and the z-axis is going through the radius, where this is the y-axis or the diameter. So, you know, a hoop can spin like you're driving a car on the steering wheel about the z-axis, but the hoop can also spin around the y-axis or its diameter, or it could even flip and spin around the x-axis, which is still its diameter, just on its side. Okay, so all of these fancy equations will be provided. Don't fret about remembering all these, okay? All right, so when you're looking at the moment of inertia, we also need to think about what is the unit. And this is where it gets weird. Like the idea of moment of inertia being like this factor of how the mass is distributed, it begins to kind of make sense as you watch the disc versus the hoop, as you watch different things spin. But look at the unit for the moment of inertia. Let's go back up here. So if the moment of inertia, so if this is our moment of inertia I, and its mass, kilograms, times r, the distance, radius, meters squared. So you get kilogram meters squared. Now, honestly, when I start thinking about the unit, you know, and like what the unit means, I can, you know, meters per second, all right, that's a rate of position change. But kilogram meters squared makes moment of inertia feel even weirder to me. So whenever you begin to try to assimilate what does this mean in your brain, I want you to think about it. It tells me how much inertia, so inertia is the tendency of an object to stay in its constant state. So it's Newton's first law. You know, for an object at rest stays at rest. An object in motion stays in motion until an unbalanced force acts on it. So think about inertia. In order to get something going, you have to apply this unbalanced force. Well, think about something that is big and massive and you want to spin it now. So that big massive thing is going to have a lot of inertia, but it also has a lot of this rotational inertia. If you take that same mass object and you make it real skinny, make it a nice skinny small radius cylinder, it's a lot easier to get it to spin. So whenever you're thinking about this whole moment of inertia, it's how easy it is to get this distribution of mass to start spinning. Okay? All right, so with that, what we have here is that overall, the rotational, I don't even know why I did that, the rotational kinetic energy is 1/2 I omega squared, where I is like the rotational analogy to mass. It's not just how much mass you have anymore, but it's where it's located to. And omega describes how that whole system, the whole thing is rolling, how it's spinning. And we have to be careful because sometimes an object can move without rolling, or it can be moving and rolling, or it can just be rotating. Okay? So you have to really read and be careful. Is this object just spinning, or is it rolling and moving? How is it behaving?